One of my favorite toys from childhood were water rockets. The little plastic rockets that you put some water in. See the water there? And then you take it and pump it up. And then launch it. How they work, of course, is the water squirts out the bottom, giving some acceleration to the rocket, and then it coasts up and comes down. The path of this rocket is described by integrating that force, the acceleration, and then integrating, that gives you velocity, and then integrating again. So take two antiderivatives, and that'll give you the path of the rocket. So let's be a little bit more formal about what we mean by an antiderivative and what we mean by how we compute an antiderivative. So, if f is a function, an antiderivative of f is, well, it's another function. Capital F, for which capital F prime of x is equal to f of x for all x in some domain. Okay, well, we now know something about, from the fundamental theorem of calculus, we know something about antiderivatives. In particular, if f is piecewise continuous, we know the fundamental theorem of calculus says that I can write a to b, f of, let me call it t dt, is equal to f of b minus f of a. Well, that's okay, but one of the neat things that comes right out of this is the fact that if I were to replace this b with an x and move this f of a onto the other side, well, I've gotten back my f of x, and this function here, by the fundamental theorem of calculus part 2, if I take the derivative of f of a plus this expression, I'll get back, well, the f of a is a constant, so that's 0, plus this derivative, and it's just what the fundamental theorem of calculus part 2 says. This is f of x. So that means that this expression we've got here is an antiderivative of f. Cool. All right. So how does that tell us how to draw what an antiderivative looks like? Well, let's go back to that water rocket. That water rocket has got a certain amount of acceleration, and over time, actually, I'll put this axis up here. Initially, the water rocket is not doing anything. It's just sitting there in my hand. And when I release it, it starts accelerating abruptly. And it accelerates for a while, and then once it runs out of water, it starts to fall. In fact, it starts to fall perhaps a bit less of a rate. It starts to fall for a while, until finally it hits the ground. So let's annotate this.
This is the launch. This is the powered. And this is where it's falling. And this is where it hits the ground. Okay. Now, if I wanted to draw the antiderivative of this, let's call this a of t for acceleration. I want the antiderivative of a of t. We know that the velocity, v of t, if I take the derivative of it, I get a of t. So I need an antiderivative. So let me draw that. Let me draw v of t. Well, initially its velocity is 0. It's not going anywhere. And then what happens is we start picking up area from here. So we take out a little bit of area. Initially we don't have very much area, and then we get some more and some more and some more. And finally we've picked up a certain amount of area, the area of this particular region here. Just looking at the graph paper here, it looks like I've got about 3 blocks. So it looks like my velocity goes up until I'm 1, 2, 3 blocks high. At which point I start to come down. Looks like 2 blocks per unit. 2 blocks per unit, 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 until finally I get to the time where it hits the ground. What happens when I hit the ground? Well, actually my plot here isn't quite right. It hits the ground. In fact, all that velocity goes away very abruptly. So there's a little bit of a spike here. This is actually the impact. And that takes all that velocity and runs that velocity back to, down to 0. Very quickly, much more quickly than I'm able to draw this apparently. There we go. So again, you've got a distinct launch and a fall. Now you will notice that what happens right here at when the velocity crosses 0, that's the point at which the orbit is or not orbit, the flight is maximum height. And so you could take the antiderivative of that as well. So let's draw that. So initially my height is 0. Initially my height is 0. This is height. And this is time. This is the antiderivative of velocity. And, well, it kind of goes up and then it starts to coast. Hits its maximum peak and then comes back down. So the thing to realize here is that here's your maximum height. That's the place where the derivative of that is 0, and indeed you can see that. Right here is where the engine cuts out. It's much harder to see. On this plot as it is here. This is the same spot. This is where the engine cuts out. And you can see that here too. That's the same point. So this little curve here kind of smoothly comes up, and then this second segment here, which I'll highlight in green, the second segment has a derivative that's linear. This is parabolic. as a parabola in free fall. And so this first segment here, this is powered. That's when it's powered, and then the engine cuts out, and it's a parabolic free fall. So, in essence, how do you draw an antiderivative? Well, you just accumulate the area, because you want to really think back to what this formula is telling you. This formula is telling you that if I want to draw an antiderivative, what I need to do is I need to accumulate area, sort of as a running tally of area. It takes a little practice, but once you see how it works, it's very easy to check, because all you need to do is take a derivative to verify that you've got the right thing. One final comment. Each time you write an antiderivative, there's an additional piece of information. That's the starting point, right here and right here. You need to figure out what those starting points are, the initial velocity or the initial position. That shows up right here as well. That's a constant. And so usually when people are computing integrals, by way of computing antiderivatives, they always say, you know, don't forget to add a constant. Most of the time people will say that that constant should be a plus c for a constant, just so that you know it's a constant. But, you know, it could be any letter you like.
Well, I've had lots of fun reliving my childhood, launching water rockets in the backyard. Fortunately, I don't know what happened. One of them, I think, might have landed on the roof or something. I mean, it's too bad. It was fun to play with, but, you know,